Host 1, picture this. We're standing inside a pristine, cool white modern laboratory. You can hear the low, steady hum of advanced machinery in the background.
Right in the center of the room, researchers are huddled over a steel table. They're wearing specialized gloves, and they are carefully, painstakingly extracting a nearly invisible fragment from an ancient, weathered piece of parchment. It's a delicate, incredibly high-stakes operation.
Which really makes you wonder, what exactly are they trying to discover? I mean, what could a tiny fragment, literally just a few milligrams of ancient animal skin, possibly reveal?
Well, what you're imagining are the very first steps of an incredible scientific investigation. We're diving into a profound mystery in this explainer. Can modern science actually determine the true age of some of the world's oldest Quran manuscripts?
But we're not going to answer that just yet, because the contrast here is just wild. On one hand, you have a beautiful, fragile, 7th century artifact covered in ancient Arabic script. And on the other hand, you have a modern, highly precise mathematical probability graph.
It's like two totally different universes colliding.
Exactly. And it brings up an immediate cliffhanger. How on earth does a physical piece of centuries-old skin translate into a mathematical curve? Well, to figure that out, we actually have to look up to the sky. Right, because this whole story actually begins high up in the Earth's stratosphere, roughly 9 to 15 kilometers above our heads. Up there, cosmic rays are constantly bombarding the atmosphere, and this interaction creates an invisible radioactive isotope known as carbon-14. You can think of it like a natural, invisible clock that exists inside literally every single living thing on Earth. Let's trace how that clock gets set. As plants photosynthesize, they absorb this carbon-14 from the air. Then, animals come along and eat those plants, taking that carbon-14 right into their own bodies.
And as long as that organism is alive, breathing, eating, growing, it's constantly replenishing its supply. It keeps its internal ratio of carbon-14 perfectly synced up with the atmosphere.
But here is the absolutely crucial part. The exact moment that animal dies, the intake stops completely. The natural clock starts ticking, and an invisible countdown begins. And because it's radioactive, carbon-14 is unstable. Over time, it just quietly decays back into nitrogen. The thing is, scientists know exactly how fast this decay happens. It has what's called a Cambridge half-life of 5,730 years. Yeah, you can picture this process like an hourglass slowly emptying out over millennia, or maybe like a battery that's gradually losing its charge. Basically, in about 5,700 years, exactly half of the carbon-14 in that animal's skin will be completely gone. Which brings us to a total modern scientific marvel. Today, using an unbelievable piece of technology called Accelerator Mass Spectrometry, or AMS for short, scientists don't even need a large piece of the parchment.
Not at all. They can take just a microscopic snippet, purify it into graphite, and literally count the number of invisible carbon-14 atoms that are left. By measuring what's remaining in that battery, they can calculate exactly how long it's been draining. It's practically a time machine.
But, as you might guess, nature isn't always a perfectly ticking metronome. Historically, the amount of carbon-14 in our atmosphere fluctuated. Things like solar storms and shifts in the Earth's magnetic field changed the baseline. So, raw radiocarbon years don't perfectly match our calendar years. To fix this, scientists use calibration curves. They literally map this against ancient tree rings of a known exact age. They compare the parchment's carbon to the tree rings to adjust for those historical atmospheric changes. But even with this amazing curve, there is still a catch. Right, which leads to a really common question. If we have this incredible AMS technology and all this tree ring data, why don't scientists just spit out an exact year? Like, why not just say the year 645 CE and be done with it?
Because radiocarbon dating provides probability ranges, not exact timestamps.
A 1 sigma range gives us a 68% confidence level that the date falls within a specific window. A 2 sigma range broadens that window to give us a solid 95% confidence. And this is so important to understand, that uncertainty isn't a flaw. It is a fundamental feature of rigorous science. It's telling us exactly what is highly probable and what is virtually impossible. Okay, so all of this naturally leads us to the most critical question of this entire investigation. With all these atoms counted and tree rings perfectly calibrated, does this mean scientists have actually dated the Quran itself?
Well, no, not exactly.
Brace yourself, because this is a massive paradigm shift. Carbon-14 does not date the moment the scribe applied the ink to the page. It strictly dates the biological material itself.
Exactly. It tells us the precise moment the sheep or the calf died to make that parchment. We are dating the animal's death, folks, not the scribe's hand.
Which introduces what we like to call the parchment paradox. You have to remember, in the ancient world, animal skin was incredibly valuable.
Right? It wasn't just thrown away. Parchment could be prepared, cured, and then stored away in a workshop or a treasury for years, sometimes even decades before a scribe finally picked it up to write on it. So the sacred text written on the page is almost always younger than the biological material it sits on.
Okay, wait a second. If the parchment is the problem, why not just test the ink instead?
It's a totally logical question, but early Islamic manuscripts generally use dark brown or black inks made from soot. And soot just doesn't contain the fresh, organic radiocarbon that's needed for this test.
Plus, extracting enough ink to even attempt a test would require destroying huge portions of the manuscript. Both ethically and practically, permanently destroying a sacred text just to test it is completely off the table. So that leaves us with a pretty big cliffhanger. If the chemistry lab can only date the skin, how on earth do we date the actual text? That is where the humanities step in to rescue the hard sciences. We have to open up the historian's toolbox to solve the rest of this puzzle. Historians use a field called paleography, which is the study of ancient handwriting, as an independent method to hunt for chronological clues.
It's like looking at the evolution of fonts. For example, you have the upright, somewhat rigid Hijazi script, which is characteristic of the very earliest texts. Then you have the much more structured Kufic script. A scribe's working life was maybe 30 years, and writing styles naturally evolved over time. By mapping these shifting handwriting styles, scholars can really start to narrow down the timeline of when that ink was actually applied.
And another absolutely crucial tool is orthography, or rasm, the skeletal spelling system of ancient Arabic. Just like English spelling has drastically evolved over the centuries, early Arabic spelling was still developing in the 7th and 8th centuries. For instance, finding archaic spelling anomalies for words like Dawood for David or shay for thing acts as a historical fingerprint. These ancient spellings independently confirm the antiquity that's suggested by the carbon dates from the lab. When you combine all of these pieces, the picture suddenly comes into incredibly sharp focus. Just look at world-famous examples like the Birmingham Quran manuscript or the Sana Palimpsest. Those manuscripts made global headlines, and not just because of a single lab test, but because the carbon dating perfectly aligned with the paleography, the orthography, and the codicology. The Birmingham manuscript's parchment was radiocarbon dated with 95% probability to between 568 and 645 CE. And the Sana Palimpsest showed similar astonishing antiquity. They attracted worldwide attention because the hard science independently verified the historical and textual analysis. Together, these totally independent methods form a holistic, undeniable picture of their early origins. Now, sometimes critics will see a probability range and claim that radiocarbon dating is an imprecise science. But acknowledging a margin of error isn't imprecise. It is literally the definition of the scientific method at work.
Exactly. True historical clarity doesn't come from a single magic number spit out by a machine. It emerges respectfully and carefully when independent methods from physics, chemistry, and the humanities are combined. That is the real beauty here. History isn't just one discipline. It's a massive, beautiful collaboration.
The scientific method is truly extraordinary. It allows us to look at an invisible, decaying atom and see deep into the human past, breathing life into the history of ancient texts.
It's been an incredible journey exploring this with you. So we want to leave you with this to think about. If you could take this incredible technology and carbon date any manuscript in human history, which one would you choose? And what profound question would you hope it could answer?